All right, hi guys. So this is lecture 2. It's going to be on logarithms. So I still don't have a better microphone, but I do have my iPad set up, and so hopefully this will be easier to watch than a piece of paper. Anyway, let's get started. So what we need to look at today are logarithms and derivatives of logarithms. So derivatives of logarithms and logs. Derivatives. Okay, so how are we going to do that? Well, there's a few ways to go about it. One of the ways involves something that we haven't gone over yet, and so we're not going to do that. Let's just define logarithms. Logarithms. So you know this, right? Like if you say if a to the x equals y, then log base a of y equals x. Okay, and that's basically your definition of what a logarithm is, and you can use that. It's not too useful, but for example, how would we do that? Like if I say, example, what is the log base 3 of 3 to the 5, right? And just looking at this, you can say, oh, okay, so if you just imagine that this was a 3, well, yeah, you imagine that this was a 3 to the x, and then the y is what's inside the logarithm, so this is a 3 to the x, 3 to the 5th, I have to redo that now. 5. So if you had 3 to the 5th equals 3 to the 5th, and then according to the next line here, the x, which is the exponent, is what the answer is, then log base 3 of 3 to the 5th is 5. And, you know, that's, I don't know if that's the most useful way to understand it, but that's what you should understand about them. You can do it this way too, using algebra. So if I say evaluate, let's say log base 2 of, I don't know, 32, for example. What you really want is you want it written the way we had the previous one here, where you've got the base of the log there, and in the thing you're taking the log of, you see the base. See the base. That's how you want it if you're going to evaluate a logarithm by hand. So what you would have to do here is you would want to realize that 32 is a power of 2. And then you could rewrite it. So the log base 2 of 32 is the log base 2 of, you can use a calculator or something to help you. 32 is 2 to the 5th. So what's log base 2 of 2 to the 5th? It's 5. Now why is that 5 and the last one's 5? I don't know. Just happened. Okay? And so that's how you're going to evaluate logarithms. Now, first thing that the homework's probably going to make you do, I mean, it could be the first or the second thing depending on how it is, for you specifically, is you're going to need to be able to graph a logarithm function, see what it looks like. So, plot a logarithm. So it's easiest to do this with an example. So example, plot, let's say f of x equals, we're going to go with log base 3, why not, of x. Okay, so that's what we're going to try to plot. Now, the way you do this is you need to make a table of values, just like you would for plotting just about anything. Make a table of values. However, you don't want to just use any random x values. You want to use special x values, right? Because if I say, if I made a table of values like this is not the one I'm going to use, and I go like 1, 2, 3, something like that, and then you have log base 3 of x. When you get to this middle one, you'll have log base 3 of 2. And you're not going to know how to calculate the log base 3 of 2 by hand. You could do it if you had a calculator, but generally you don't want to need to use a calculator for these problems. So you have log base 3 of 2, you don't like that. The reason the 2 doesn't work is because, remember, you want your stuff to be set up to where you have the base there and there. And so what that means is when you pick x values, you should pick, why did I do that? I don't want highlighter. When you pick x values, you want them to have the base appearing. So that was kind of long-winded, but what I mean is this. So if you're making a table of values, I'll make it horizontally so it fits on this page. Close enough. X log base 3x. What you should do for your x values is you choose them so that they're all powers of 3, right? Why 3? Because the base is 3. So that means that you should do this. Like, what x values should I use? I should use like 3 to like the -2, 3 to the -1, 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3. Then when you take the log of them, right, you'll have stuff like log base 3 of 3 to the -2. And what is that? -2, right? Because that's how these work. We've seen that now a couple of times. So that makes these this table very easy to fill out that way. -1, 0, 1, 2, 3. So the y values are simple values and the x values are a little bit more complicated. Now, once you have your table of values, of course, you just go and you plot it like you would any other function. So let's see if we can do that. So let's try to plot this. Oops. Why am I so bad at this? So what I'm doing here is, it looks like for the y values, I went up to 3. And for the x values, the biggest one is 3 to the 3, which is 27. That's not even going to probably fit on here. But the next biggest one is 9. So let's just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Wait, what? Yeah, that's fine. Okay. That to 5. All right. So that's the graph that we're going to use. Now, then we just need to go through and plot points. Now, you do need to understand, exponents in order to do this, right? Like, for example, what is 3 to the -2? You need to understand that that is 1/9. 3 to the -1 is 1/3. 3 to the 0 is 1. 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27. So those are my x values. All right, let's make a plot. So the first point is 1/9 -2. So 1/9 -2 is about here. It's very close to 0. But that's my first point. My second point is 1/3, -1. So that's about like this. My next point is 1, 0. It's there. Right, we're doing that one. Now we got to do this one, which is 3, 1. Then we got 9, 2. And then the next one would be way over at 27, which is, somewhere, over here. And that would be up at 3. And I'm not going to bother putting this in exactly the right spot, but somewhere over there. And so when you connect the dots here, what you get for your graph looks something like that. All right. And so what you've got is a vertical asymptote right here at 0. Y equals 0. It sort of flattens out. You can see that the curve sort of flattens out in this direction, but it doesn't flatten out completely. It keeps going up forever, and that's your graph. Okay. And yeah, so you should be able to produce a graph like this. If you're trying to just pick off a multiple choice graph the correct value, or if you're trying to pick the correct graph out of a list of graphs, you don't need to plot so many points. If I had this point right here, and this point right here, and this point right here, then I probably could tell which was a correct graph if I had a multiple choice question asking me. If I couldn't, then you just add one there and add one there, and that would be definitely enough. So you just plot 3 or 4 points. You need to make sure that your x values that you choose are powers of the base. Okay? And that's how you make a graph. Now, some algebra with logs. Now, you're going to need to know these properties here. Properties of logs. Okay, so what log properties do we need to know? You should have learned these at some point in the past, but in case you didn't, here we go. So if you ever have a log, and it doesn't matter what the base is, so I'm not writing it, but if you ever have a log of AB, that can be split up into a log of A plus the log of B, like so. If you have a log base A divided by B, whatever A and B are, that's a log base A minus a log base, not base, a log A minus log B. The base is whatever. All right, does have to be the same, so maybe I'll write it in. They're all A, little a, little a, little a. All right, so there's 2 properties. You use those a lot. What's another property? Another one that shows up a lot is log of A to the B. You can take that exponent down in front, like so. Again, little a, little a. We use that one a lot. What else? log A, let's say 1 over B is negative log A of B. And really, that's actually just a special case of the previous one, because, you know, if you think about it, then this right here is actually just b to the negative 1. And so that's just the same as rule 3, where we took the negative 1 down in front. So it's the same rule. Or you could even get this one from rule 2 as well, just by using a is 1. Okay, now having written down these kind of basic rules here, there's kind of just a couple things that we didn't mention yet, but need to be mentioned, so I'll write them right here. Oops, switch back the color. This color? Yeah. Oops, now I'm still erasing. So something that we've already used, but just to write it again, if you have log base a of a to the b, that's just b. Also, oops, if you have a to the log base a of b, that's just b as well. And so those last two are, you know, they can help you evaluate statements that have logarithms in them, basically. Okay, what else? So we haven't mentioned natural logs, so let's write a little note on natural logs. All right. So you should know that e is a number, Euler's number. Is a number. E is approximately equal to, let me grab a calculator so I can write out a few decimal places here for you. 2.7182846. Okay. So that's just a number. And so a log base e is called the natural log. Has base e. So whenever you see ln of something, that just means log base e of that thing. And other than that, you don't really need to know much about it here. You can just say, so like if you wanted to evaluate ln of e to the 5, what would that be? It'd be 5. What would ln e to the x be? Not 5. Everything's 5. That would just be x. If you have e to the ln 3, what's that? 3. Why is that 3? Because of this property right here, right? When you've got the base of the log and the exponential matching, then the exponential and the logarithm cancel. So these match. Okay? So there you go, a natural log. Hey, look, L. And that is what a natural log is. Now, the first problems that you get involving those properties are probably not going to be stuff like this. They're probably going to be simplifying logarithmic expressions or something similar. So you'll get something like this. Example. Simplify, not simplify. I should be more clear here. Write as the sum or difference of simple log terms. And I'll say what I mean by that in a second. And they'll give you something like this, like natural log, doesn't have to be natural, but this one is. 9/2 b to the 5th. And basically the idea here is when they say this to you, write as the sum or difference of simple log terms, what they really mean is just that they want you to use the log rules to break this up as much as possible. Break up into simple terms as much as you can. So you're just going to be applying those rules that we've got on the list here. So for example, I see that rule 1 here will let me split up a log when we're multiplying things in the log. So of course, this and this are being multiplied in the log. So we apply rule 1. And you're going to get natural log 9/2 plus natural log b to the 5th. Okay, so that was rule 1. But then on that first term, natural log 9/2, that's division. So rule 2 will let me handle division. So if you apply rule 2, you're going to get natural log 9 minus natural log 2. And on natural log b to the 5th, well, we've got a power. So if you look at rule 3 tells you how to do power. You can take the power down in front. So this is going to be also rule 3. There you go. And then if you look and say, well, can I break up stuff anymore? Then the answer is no, you can't. And so this right here, this is what you would want for your answer. Okay? Hey, no, why? That's what you would want for your answer when they say to write it as a sum or difference of simple log terms. I think your book actually does use the phrase expanded form sometimes. So if they do, then well, you can see what you're supposed to do. All right. Okay. So I see that also they're going to ask you about transformations of graphs. And of course, you're all in calculus 2. So you should know all these transformations, but I'll write them. Transformations of graphs. So if you have an original graph, y equals f of x, right? Then your transformations are going to be like this. So if you say, what is y equals f of x minus a? That's a horizontal shift, right? That's a shift left. Is that a shift left? Or is that a shift right? Let me think. That's a shift right, right? I don't know why I wrote that. Erase. So that's a shift right by a units. If you do this, f of x plus a, that's a shift up by a unit. I don't know why I'm using a for everything. If you do this, y equals, I guess switch variables. I'll use a k. Kf of x, that's a vertical stretch by a factor of k. If you do this, f of kx, then that is horizontal compression by a factor of k. Right? And the reason I'm just mentioning these, let's see, what else can I do? Also, you can do reflections. So if I do negative f of x, that's a vertical reflection, so it's upside down. And if you do y equals f of negative x, then that is a horizontal reflection. So it's a mirror image that way. Now, why do you care? Well, because you might have an example question like this. So they say f of x equals log base 10 of x, and then they would say stretch vertically by a factor of 10. No, actually they don't. They say 7. Shift lefty left by 4. Shift down by 5. And you know, what's the equation? Write the new formula. So you just want to combine all of these ideas, right? So if you're going to stretch it vertically by a factor of 7, then that means you want, like this, a 7 out front. So 7 log base 10 of what? Log base 10 of what? Then we want to shift it left by 4. Well, how do we do that? Well, like this, right? If you change the x to an x minus a. So we're going to have x minus 4. That's how we're going to shift it left by 4. Then they say down by 5. How are we going to do that? Well, that is like that, right? A plus a moves it up by a minus a would move it down by a. So we need to move it down 5, so that's a minus 5 on the outside of the function. And there you go. That is all of those. What? Why you do? Okay. So, I don't know why you have to do that, but you do. Let's see here. I'm just looking through the homework, and I see a question that, we've talked about what you need to do in order to do it, but we didn't do it, and I think it looks confusing a little bit, so I'm going to copy it. So log base 464 equals 3, and then they say write exponential expression equivalent to this. And when they say that, what they mean is way back at the beginning here in the notes, where I wrote logarithms, if a to the x equals y, log base a of y equals x, they literally just mean they gave you the second form, write it in the first form. So it looks like you have something complicated to do here, but you don't. All you do is that's your base, that's your exponent, and then that's the other side of the equation. So what's your answer look like? 3 to the 4th equals 64. So it's just an alternate way to convey the same amount of information. All right. So I'm clicking through here, just looking for more log stuff. See if I want to do any. I don't think I do. I think we're just about done. All right, yeah, I think we are done. Okay, so that's going to be it for this set of lecture notes and video. I'm going to be doing the one on log derivatives momentarily, so look out for that.